Okay, we're going to get started here quickly. If you would, open up to page 441. Okay, we briefly introduced this last week as we decided, well, not decided, but got back into a groove or swing of things, if you want to call it that, coming back from Christmas break last week. And as we had noted, some of this information is I'll call it repetitive, because when we're talking about these acids, we've derived them. We spend more time with esters than anything else because they're as you can see, derived from that of the acids when you react that with an alcohol. We gave a brief illustration of that last week. Okay, so as we continue to move forward, then that term carbonyl group is there. I believe these were handed out to you. Oh, okay. You don't have to write in. Okay. It's all written in for you. That's why I'm asking.
Oh, yeah, that is.
Oh, okay. Fair enough. Fair enough. Okay. So, again, and we've illustrated this before, similar to ketones and aldehydes because of this right here. When we're talking about that carbonyl group, again, that's referring to a carbon with a double bond, an oxygen then, okay? And, of course, structurally, how this tells it or sets itself apart, you've got that hydroxy or OH group attached then on the end as well. So if you were to visualize, acids are the most structurally common to esters or ketones or aldehydes. Remember, they all have carbonyl carbons, or carbonyl atoms. Okay? So think structurally, that carbonyl atom for carbon in a ketone is where? Anywhere other than that of the end. Yes. So you can eliminate ketones. So now you've got it down to either esters or aldehydes. That's correct as well. That's also correct. It is the aldehydes. Yes, they're most structurally similar to that of the aldehydes. Okay, so and again, that's why we spent that amount of time very early last semester, so you could visualize what those families would actually look like. Okay, and why we call them? I guess I don't know why the ester. You get the idea that they make fragrances or perfumes, but that's what they're essentially known for, is giving off those fragrances. And in many solvents, it's very evident that this amine group here, or excuse me, amide group is certainly attached because that gives off a certain aroma then as well. Weren't too many people washing their vehicles yesterday, but I did. And there's no lineup in there. I decided to zip on through, and hopefully this wasn't a mistake, and I don't think it was. It's still clean. It's one of the things you hate to do, but sometimes you have to get that salt off, even if the roads are still going to be bad, and you hate to do it, and then it looks just the same as it did before you washed it. But maybe I should have taken. Might have took the wrong highway in, but yeah, it's still looks good, I guess. All right. So when we look at this here, okay, even if we didn't go any further, what term does this look similar to on the periodic table? A halide, what would that remind you of? Yes, a halogen, which means you're dealing with column 7 then. And this is something that we're going to do this chapter, and we've illustrated. Uh, I'm trying to think of when that was. We took what was an alkene, hydrated it, and again just on pencil and paper. An alkene, hydrated it, and then turned it or oxidized that then to a ketone, and then reduced it back to that of an alcohol, and then dehydrated it. So, so a lot of these, as you can see, all 4 families can be synthesized and then returned back to acid. So it's kind of like a ping pong effect where you can go back and forth. Okay, I wanted to. Okay, we will stop there for today, and then we'll look at page 441. Does everyone have this information that wants it? Okay. Then we'll get this wrapped up, and that'll be it for today. 15. And there again, what sometimes happens is this is utilized from a soft cover book that doesn't have the general chemistry in front of it. That's why it says chapter 7 in front, but it's actually chapter 15. So as we look at page 441, there you can see all of the different families that we have talked about so far, where it's talking about your ester. We didn't do any acid halides or amides, but the main one is that of the ester. Okay, and on that table, you see, okay, the family got acid, ester, and those are the main 2 that would look familiar. But what we want to do now is we'll introduce how to, per se, name these, which is really no surprise because it's always going to follow a general pattern, and this is one that's going to repeat itself then as well. So on page 444, okay, it says rules for naming carboxylic acids. Okay, so you find the longest continuous chain. That's been a repeating pattern since the first week as well. And then you have to find the carboxyl carbon, again, which would mean the one with the double bonded oxygen. That's no surprise there. You change the suffix, in other words, drop the E and then change it to OIC. Nothing different there, or no surprises. The names of the substituents are used as prefixes. Okay, that's the same, preceded by numbers to indicate their positions on the longest chain. That's nothing new. So if we had, per se, pentanoic acid, so if we had a CH3 group on the second carbon, you would say 2-methyl pentanoic acid. So again, that's nothing new. A compound with 2 COOH groups is named as an alkandoic acid. We really don't spend too much time on that. We did maybe with 2 OH groups or 2 double bonds, but that's not going to be the case here. But finally, the last one, the aromatic compound That's no surprise, benzoic acid. And we spent some time with that last semester. But then when you look down at the bottom on table 15.2, you'll notice that probably for the most part, you'll be referring to these as common names. Not in here. We're still going to use the scientific name because that's what you'd be more familiar with. In this case, one of you is going to have to probably make that transformation next year. Next year, 2 years from now, where you may be sitting in a class and a professor or a teacher's assistant, rather than saying methanoic acid, would say formic acid. Okay, and acetic acid, they may say even vinegar rather than ethanoic acid. Or there is nothing for propanoic acid. Notice those are the same. Butyric acid, we get to deal with that. That's your smelly materials. That's like vomit, for instance. And then oddly enough, they really jump up from, as you can see, 1 carbons, 2 carbons, 3 carbons, 4 carbons, and up to 10. And once you get past them, that fourth one, there really are no common names to that. Okay, tomorrow we will start talking about some of these physical properties, and then spend a little bit of time on see how these carboxylic acids are used in nature. And unfortunately, last semester we we didn't make that lotion. We made soap instead. And what I want you to do briefly, this will be the last thing we do, look at page 448. So what you're seeing there is a synthesis for making soap, because soap is essentially a carboxylate salt. So what we did, rather than we used an oil, which was certainly vegetable oil, and then reacted that with sodium hydroxide, which essentially is a strong base, okay? And notice, what do we say all these reactions is all about the what? And what do you notice in this reaction? What's happening? Yeah, your water is given off as a byproduct. That is correct. So with that, it probably would have made more sense to do that this semester rather than last, but I kind of dropped the ball on that. But here we are. We do make some of those fragrances or esters, and that actually works out pretty well. The soap activity, I think, did turn out all right for some of us. It's actually still there. So we will continue with these acids tomorrow. So we'll catch up to you next time.